Euclid's Elements, Book 3, Proposition 22. Opposite angles of quadrilaterals in circles are equal to two right angles. So if we have a given circle, circle ABCD, and we also have a quadrilateral ABCD, then I say that the opposite angles, so the angle at A plus the angle at C will equal two right angles. Likewise, the angle at B plus the angle at D together will equal two right angles. So this is what we're going to prove. So the first thing we'll do is we will connect the diagonals, AC and BD. And now let's look at this triangle, triangle ABC. So in triangle ABC, we obviously have this angle, and this angle. And I'll just call them angles 1, 2, and 3. And we know that angle 1 plus angle 2 plus angle 3, because they're the interior angles of a triangle, they're going to equal two right angles. We know this from Book 1, Proposition 32. That's the sum total of the interior angles of a triangle. So that's our first step. Our second step is we're going to invoke Book 3, Prop 21, the previous prop. And this tells us that when angles are in the same segment, then they're going to have the same value. The angles are going to be the same. So if we look at this segment here, and the segment is right here, we can see that the angle here at 3 is on this segment. And likewise, this angle here at D, I'll just mark it. This angle here, okay, we'll call this angle 4, but it's going to be the same. It's an angle in the same segment as this angle 3. And therefore we know that they're equal. So angle 3 is equal to angle 4. Likewise, if we look at angle 1 here is standing on this segment. It's an angle in this segment. And this angle here, I'm going to mark it angle 5. Angle 5 is also standing on that same segment. So it's another angle in the same segment. So for that same reasoning, we know that angle 1 is equal to angle 5, which means the combination of these together. So angle 3 and plus 1 is equal to angle 4 plus 5. So to both of these, let's add the angle 2. So if we have equals and we add equals, then the remainders are equal. So we're going to add angle 2 to both sides. And that gives us angles 3, 2, and 1 are equal to angles 2, 4, and 5. But we already know that the value of angles 1, 2, and 3 are equal to two right angles. So we say this is equal to two right angles. And since it's equal to this, then this must also be equal to two right angles. But angles 4, 5, and 2 are simply the angle at D and the angle at B. So they are equal to two right angles. This is equal to angle D plus angle B. Similarly, we can do the same thing to show that the other, so we'll do that really quickly here. So we'll just mark off a different triangle here. So whereas before we used this triangle, now we're just going to shift over and we're going to use a different triangle. So let's use triangle DAB. So in triangle DAB, let's do a different color, we know that this angle, angle 1, and this angle, angle 2, and this angle, angle 3, are altogether equal to right angles. So 1, 2, and 3 equal two right angles. Again, Proposition 32 of Book 1. And as we did before, we're going to notice that this angle is on the same segment as this angle. So this angle 4 here will be equal So angle 1 is going to equal angle 4. And we're going to notice that this angle here is the same, it's standing on the same segment as this angle 3. So this is going to give us angle 5 equal to angle 3. So we can add these together. So we know that 1 and 3 is going to equal 4 and 5. And as we did before, we're just going to add the remaining angle 2 to both sides. And that is going to give us that angles 1, 2, and 3 equal angles 2, 4, and 5. We know angles 1, 2, and 3 are equal to 2 right angles. Therefore, 2, 4, and 5 must be equal to 2 right angles. Oops, there we go, 2 right angles. But angles 4 and 5 and 2 are simply angles C and A. Therefore, angle A and C are equal to 2 right angles. And therefore, the opposite angles of quadrilaterals in circles are equal to 2 right angles. And that's what we're given to prove. And so we've done it, so we conclude QED.